on behalf of Space Education and Research Foundation, and on my personal behalf, it is my pleasure to welcome Professor Arup Dasgupta and all the participants from different countries to this webinar on satellite communication. Today is the second talk of this series on satellite communication, and today's module is Introduction to Satellite Communication. And before I hand over the mic to Professor Arup Dasgupta, I will say a few words of his introduction. Though I introduced him yesterday, and this is the second talk, but it is customary to introduce the speaker before the talk, so I do that. Professor Arup Dasgupta had a very excellent academic career, did his master's in engineering in electrical communication engineering from Indian Institute of Science, Bangalore in 1970, and he then joined Space Application Center at Ahmedabad. He is currently managing editor of Geospatial World magazine, and he was adjunct faculty in two institutes, DAIICT and CEPT CEPT. He has a very long experience of 48 years and excellent experience in satellite communication, remote sensing, and GIS technologies. In 2005, he retired as a deputy director, Satcom and IT applications area of Space Application Center at Ahmedabad. After that, he served in two positions as a distinguished professor at BISAC from 2005 to 2009, and from 2009 to 2014 he was an independent director in ScanPoint Geomatics. He has, for his very distinguished and excellent contributions to space technology and space science, he received Excellence Award for 2005 from Indian Society of Remote Sensing, and for 2016 he received it from Indian Society of Geomatics. He is also a recipient of Geospatial Lifetime Achievement Award in Geospatial Technologies for 2009 and Astronautical Society of India's Award for Space Science and Applications for 2000. He is a senior member of IEEE and fellow of IETE, fellow of ISG, life member of INCA and ISRS. His current interests are space policy, convergence of space and information technology for sustainable development of the planet Earth. With these words, I now invite Professor Arup Dasgupta to join the room and deliver his talk on satellite communication. Professor Dasgupta, please.
Thank you, Dr. This is the second lecture that I am giving. This is on basic introduction to satellite communications. So let's begin. Again, what we are going to talk about is going to be a little bit of history, and this deals with the paper written in 1945 by Arthur Clarke, and this paper appeared in a magazine called Wireless. And for those of you who know him, Arthur Clarke is a very famous author of science fiction. He's written books like 2001, A Space Odyssey, and in 2010, Space Odyssey Returns, and then Rendezvous with Rama, and quite a few other books. Then we will go to understand certain basic principles of satellite communications. And then we will talk about the growth of communication satellites from 1963 to the present. Okay, so the earliest idea was from a person called Arthur Clarke, and he wrote this paper in 1945, and he opined that by using 3 satellites in geostationary orbit, we can have intercontinental communication. Remember, 1945, rocketry had just taken baby steps. In fact, the most famous rocket at that time was the German V2 rocket, which was being used to pound London and other UK cities. And Arthur Clarke thought that this was also it was also possible to use such rockets to send satellites into space, and if you could set it out far enough such that the angular rotation of the satellite and the angular rotation of the Earth remain same, then the satellites will appear stationary above the Earth. So that's why the name geostationary satellite. But then, as you see, that at that time in 1905, the technology was so new, in fact in its infancy, that Arthur Clarke himself said that it could be realized in another 50 to 100 years. So he envisaged that this would come about from between 1995 and 2045. That was his estimate at that time in 1945. So here is the concept. So you have the orbit, and this is the geosynchronous orbit. Satellites are roughly at about 36,000 kilometers from the Earth, and since they are rotating at the same angular speed as the Earth, that's why they remain geostationary. And in honor of Clarke, this orbit is now called the Clarke orbit. So how is the orbit calculated? A little bit of mathematics. Now all of you know Kepler worked on the two-body problem, and the third law which Kepler had postulated was that the square of the periodic time of orbit of a body around another is proportional to the cube of the distance between the centers of the two bodies. So the law says that the square of the periodic time of the orbit, let's call that n, of a body around another is proportional to the cube of the distance, okay, between the two bodies. Okay, so here in the diagram what you see is k, the constant is the Earth's gravitational constant, and since the Earth rotates west to east at a speed of 3.62 pi radians per day, therefore geostationary orbit, the distance is E plus h. You see, you have to calculate from the center of the Earth, right? So you have the radius of the Earth, and then you have the height of the satellite above the Earth. So h is the height of the satellite above the Earth, and this is the radius of the Earth. So we have d defined as E plus h, and the orbit is of course 2 pi divided by 1 day. If I put these numbers into that equation of d cube is equal to k by n squared, where k is the gravitational constant, then you will get h equal to 35,786 kilometers, which is as close as I can get to 30. So normally we round it off to 36,000 kilometers. This is important to know because this is the only orbit where you can have a geostationary satellite. So what kind of satellite links do you have? This is a very schematic diagram. We have an Earth station, we have another Earth station, and this Earth station uplinks a signal to the satellite and receives a downlink, and same way here this satellite uplinks and again receives a downlink. So the message from here will travel here, a reply message from here will travel here. Okay? This is very simple. Okay, now let's go a little beyond that. So typically, if you look at a communication satellite, what you have? So you have this is the communication satellite in a very schematic format. So we put everything else together. So you have a propulsion system, then you have the solar arrays for the power, then you have a lot of stuff for the management of the satellite. What is of interest to us is the transponder or the communications payload, right? We call it a transponder. Why do we call it a transponder? I will let you know. Why? So when you uplink a signal, it passes through a filter, a preamplifier, and then it goes into a down converter, right? Then again goes through a high power amplifier filter, and it is downlinked. And this whole thing is called a transponder. What it does basically, why we call it a transponder, is it takes a signal coming in at a particular frequency, it down links to down converts it to another frequency, and then retransmits it. So this is also termed as a bent. If you imagine a pipe in space, so your signal goes into the pipe, it changes frequency and comes back again, right? So it is called a bent pipe transponder, right? So this is the earliest kind of transponder that are there. We'll discuss about other transponders later. So what is the goal of the satellite? The goal of the satellite and the link is to deliver messages from point to point or point to multi-point with acceptable fidelity. That means acceptable quality. Now, message could be anything, as it was audio mainly, but now with video, you send data and so forth. So you have to optimize both the quality and quantity of the messages, and optimization has a cost associated with it. So the factors which affect the link design are, for example, the satellite weight and size, because the launcher has a fixed capacity. So because of that, the satellite size is and weight is, and therefore the amount of power that the satellite can generate through solar arrays is limited. The high power amplifier that you can put on is also limited. The size of the antenna is also limited. But also these factors then impact the signal strength available from the satellite to the ground. Right? So we have to look at all these things together. So what are the important parameters in a satellite communications? One is multiple access. The satellite signal should be accessible to many people. There should be a certain performance standard. Now the performance standard is measured by a guaranteed minimum signal to noise ratio. We will look at the signal to noise ratio in detail. And then the optimum use of the RF bandwidth and the power, because you are very much power limited, bandwidth limited. So you must make the best use of the power that you have and the bandwidth that you have. Signal noise ratio depends on another parameter called the carrier to noise ratio. Okay, so that is on the RF channel, the carrier, and there is a certain amount of noise mixed with it. So the carrier to noise ratio again defines the quality of the signal that you get, and the carrier to noise ratio it depends upon the kind of modulation that you are using and the kind of receiver bandwidth that you have at your disposal. So let us remember these parameters, because we will be discussing these in a little greater detail. So here is this basic satellite link. Again, as I said, you have satellite transmitting. It receives the signal with a low noise amplifier. Why low noise amplifier? Because the signal is traveling 36,000 kilometers from the Earth's surface, right? So it reaches, by the time it reaches the satellite antenna, it's pretty weak. So you have to have a low noise amplifier. Then you convert the frequency, and then you pump up the power using a high power amplifier, and then again you send it back to the Earth station. And again, remember, 36,000 kilometers is the amount that distance traveled. So here again you have a very low signal, and therefore here also you need a very low noise amplifier. So some of the important parameters are relating to this are, first, something called the effective isotropic radiated power. That is the amount of power that is being radiated by the Earth station and by the satellite. And then something called a G by T. Okay, we will talk about this G by T. G by T is a kind of measure of the system quality. Okay, we have signal to noise ratio, we have carrier to noise ratio, and we have G by T. Then of course the bandwidth is always very important. Then there is something called a path loss, and there are other losses, and we will be discussing these over the next few slides. First, let us talk a little bit about isotropic power. What do we mean by that? Isotropic radiated power is the power radiated from an ideal point source in all directions, right? So you have a point source and it is radiating out power in all directions, right? Then, what is that is the power which we call as PT, let us. Now imagine a sphere around this isotropic source whose radius is r, right? Now I take a small area of that sphere and I try to find out how much is the power going through. So one can talk of a term called the flux. Okay, that is the amount of power going coming from the point source and reaching the what you call this vertical area, right? Okay, so we have the flux, and that is equal to the power transmitted PT divided by 4 pi r square. Why 4 pi r square? 4 pi r square is the surface of the sphere of radius r. So then this becomes units are watt by per meter square, right? And this is called the flux. The flux is therefore is the amount of power passing through a unit area from an isotropic source at a distance r. Now clearly you will understand that the more it increases, the less the flux is, right? And this is a very important point you have to note. Okay, now we come to another antenna gain. Now the antenna is basically a passive device, so how do we talk about gain? Okay, the antenna gain is the ratio of the antenna flux to the flux density of an isotropic radiator. Okay, so there is something wrong here. Okay, the flux density, what I mean is the antenna has a beam, right, pointed in one direction, and it is pushing that entire power through that beam, right? Now supposing I had, instead of that antenna which is sending action, I have the isotropic radiator. To get that same amount of power, what would be the size of the isotropic source, right? So then the power of that becomes defined as at a distance r. Okay, it gets defined as P is the antenna gain gets defined as the power at a distance upon the isotropic power by 4 pi. Okay, so PO is the total power radiated in all directions. This is imaginary. It is not, that is not what the antenna is doing. The antenna is sending the power only in one direction. But I am imagining that I have an isotropic source which is sending the power in that amount of power which is having the same flux density as the antenna. When that happens, then the you have the effectively the antenna having a gain. So if the antenna gain is really a measure of the sharp beam of the antenna, right? So therefore we define it as the power P in the direction theta with which the antenna is pointing, divided by the isotropic power, and that isotropic power is going over the entire 360 degrees solid angle. Okay. So this is the antenna gain. So we now come to the effective isotropic radiated power. So if I have a transmitter of power PT, which is connected to a lossless antenna of gain G, then the flux density at a distance R along the bore side is the direction of the antenna, is given by the product of PT and GT and divided by 4 pi R square actually. Okay, so this becomes the flux density, right? So the term PT-GT is called the effective isotropic radiated power, right? And it represents an isotropic source power equal to PT-GT. Is this point clear? I will again repeat. An antenna has a beam and it is pumping that power into that beam, say in some direction. But if amount of flux that is reaching a distance R is made equal to the power coming from an ideal isotropic source, and that ideal isotropic source would have to have a power equal to the power transmitted by the antenna multiplied by the gain of the antenna. See, so this is how we compute the effective isotropic radiated power. Okay, so now what is the received power? So the received power at a distance R using an ideal antenna of aperture A is PR, let us say, right? So this is an ideal antenna, it has losses, and then received power is equal to flux into the area of the antenna. This is fairly simple, right? The antenna has a certain area which is catching the radiation. That area is A. The flux density is given. So multiply the flux density by the area of the antenna and you okay. So now the actual calculation for an antenna of physical size AR and efficiency eta. Now we are talking in terms of a non-ideal antenna. So the non-ideal antenna will have certain efficiency which is to be taken into account, and then what you have is a effective antenna area which is equal to eta times the actual physical size of the antenna, which is AR, right? Now let us see how the power received will look like. So the power received is flux into area, and flux is equal to PT GT by 4 pi R squared. So PR, the received power, is PT GT AE divided by 4 pi R squared. Okay, and from the theory we know the antenna gain is 4 pi AE by lambda square, which is lambda is the wavelength. Okay, so if I substitute this over here, then I get the received power is equal to the transmitted power, the gain of the antenna, the gain of the receive antenna, the lambda square divided by the 4 pi R square. Okay, so this is the actual power received by the antenna. Now from this we come to an equation that is equal to PT GT GR by 4 pi R by lambda square. This term 4 pi R square by lambda square is called the path loss. Okay, this is very easy to understand. As your power is going through space, it is getting more and more diluted. The further you go, the more diluted is the received power, and this dilution is purely because of the distance. The further you are away from the satellite, the more the distance, therefore more the path loss. Path loss is a very what shall I say, a very normal thing to happen, and it is not related to anything which are in terms of the noise and things like that, right? We later in the presentation. Okay. So the power received is now as the EIRP, that is PTGT, into receive antenna gain, which is GR, divided by the path loss. Now, normally when we work in communications, we normally use logarithmic base. We don't use the actual numbers, we use logarithm. So, if I express this in terms of log to the base 10, then the received power is equal to EIRP plus antenna gain minus path loss, and expressed in dB watts. So, EIRP is again 10 log to the base 10 PTGT, and GR is again 10 log 4 pi A by lambda square, and path loss is equal to 20 log 20 times log 10 4 pi R by lambda dB. You remember the LP is squared, so when you take it to a log, it becomes 20. Okay. Okay, so this is called the Friis transmission equation. It's very basic. We now get into more complications. So let us see now a typical satellite to earth link, right? So here is a satellite, it is transmitting PTGT, EIRP, and this signal is being received by the by an antenna of gain GR, and it is passing through a distance of R, which is the 36,000 kilometers, and that is giving rise to a path loss LP. Now there is also certain amount of loss in terms of the transmission, which I will call as L of T loss in the transmitting antenna. Then there is something called the atmospheric loss. Okay, in my last lecture I had said that atmosphere also helps us but also hinders us. We will look at this particular aspect in this case. Then we have the receive antenna, which also has some efficiency. So there is a loss in the receive antenna, and therefore the power received by the ground antenna to EIRP plus the gain of the receive antenna minus the path loss minus the atmospheric loss minus the loss at the transmitting antenna minus the loss at the receiving antenna, and thus this is a logarithmic scale expressed as a dB watt. Okay. Now again the reverse is also true, because when I am transmitting to the satellite, again I see the same thing, that the power which is received at the antenna is again the EIRP of the transmitting antenna on the ground plus the gain of the antenna on the satellite minus the loss due to the path minus the loss due to the atmosphere minus the loss at the earth station minus the earth loss at the satellite, and again in log terms it is expressed in dB watt. So it's exactly the same both ways. Okay, now let us start looking into this link equation more detail, right? So LP, as we have seen, is called the path loss. It's not really a loss but a reduction in signal due to the signal spreading with distance from the source. LA is the atmospheric loss, LTA is the transmission antenna loss, and LRA is the receiving antenna loss. Now let us come to the noise. There are several types of noise. So there is antenna noise, which is related due to sky noise, due to atmospheric absorption, due to rainfall. Then there is man-made noise, thermal noise, earth radiation noise. In communication, noise degrades the signal reception, and the effect of all these noises is clubbed together under the term system noise. Okay? So system noise is characterized by something called a noise temperature. This is a new concept that I am introducing at this point. Noise temperature. Okay, now in satellite communication systems, the noise is of different types. First of all, since the signals are very weak, hence noise has to be reduced to a minimum. Now the intermediate frequency band is set to just pass the carrier and the sideband. Right? Remember, I have talked to you earlier. When you modulate, then you have the bandwidth is set to be just enough to pass the uh, the carrier and the sidebands. Right? Now, the equivalent noise bandwidth is not known, so the 3 dB bandwidth is used. Okay, and the error is small if the passband has a sharp roll-off. Okay, what do I mean by sharp roll-off? That is, you have a passband and then you can have a slight roll-off. It's not exactly sharp like that, but you can make it as sharp as possible. Then keep noise temperature very low by using very special devices like gallium arsenide FETs, and or earlier we used to use parametric amplifiers. Typical noise figures in such a system will be the order of 70 to 200 degrees Kelvin. Okay. Now, the noise power in a system is the total thermal noise in the system. It is represented by a noise source placed at the input of a noiseless receiver such that the output noise remains the same. So Pn is equal to KTS/BG. So Ts is system noise temperature, B is the bandwidth, and G is the overall gain from the antenna output to the demodulator input. Okay, so the RF and IF stages are basically included. So this then defines me the thermal noise of the system. So in a typical communication system, what you have is you have a transmitter which is transmitting PT/GT, the EIRP. You are receiving it with the antenna gain GR, and it gives you a per PR. Now you have a low noise amplifier, and this has its own gain at the RF frequency. Then you have a down converter, and that has its own gain. And then you have the intermediate frequency amplifier, okay, and then it goes to the demodulator. So in the entire chain of these are included in the noise calculation. So the antenna delivers a carrier signal power PR to the input of the RF stage. This power is multiplied by the system gain and delivered to the demodulator input. The system gain is composed of the gain of the low noise amplifier, the down converter, and the intermediate frequency amplifier. So the carrier to noise ratio at the demodulator input is thus C by N, and that is PRG, that is the received power times the antenna gain divided by KTS/BG, which is the noise component, and that is nothing but PR by KT. Right? So this is a very important parameter, the carrier to noise ratio, for characterizing any communication link. Now, for each earth station, we define a figure of merit G by T. Okay, that is, the G is the gain of the antenna and T is the noise power. We know that C by N is PRG by KTS/BG, which is equal to PR by KTBS. Right? So this is what we calculated in the previous slide. And Friis equation also we remember is PTG TGR divided by 4R by lambda whole square. Now substituting this into the C by N equation, we get an expression PT GT GR divided by KTSB into lambda by 4 pi R whole square. And then if I further do a little manipulation, PT GT, take out GR from here, KB, take out TS from here, and lambda by 4 pi r square, that remains the same. Now the point to note here is that for any given satellite system, PT, GT are constant, KB is a constant, lambda by 4 pi r square is also a constant because you are at a distance of 36,000 kilometers. So what the carrier to noise ratio, that's the quality of the signal, which will decide your signal to noise ratio, is the GR by TS. This popularly called the G by T ratio. And this is a measure of the figure of merit of any earth station antenna system. By the way, I'm sorry, I seem my voice seems to have been cut at some point of if you need any clarification during that time, again I'll do it during the question answer. So how do you choose the frequency? Well, if you have lower frequencies, then don't have so much of atmospheric attenuation. You see, for example, C band, which is basically 4 and 6 gigahertz, there is hardly any atmospheric attenuation. But then you need very large antennas because you need high pointed beams. At lower frequencies, your bandwidths are not so much, and typically they are in the 6 by 4. But now, because of the great demand of data, people have been forced to move to higher frequencies because you get more bandwidth there. But antenna sizes become smaller also, and that's a positive point. For example, your DTH home antennas are just about what, less than a meter, right? But they work in the high frequencies, and when it rains and the rain rate is high, you lose your signal. So 11 gigahertz band, which is your basic frequency for the DTH, you will lose the signal if there is a very high rain rate happening. But there are techniques which people are using to be able to overcome these difficulties. Okay, so again let's go back into a little bit into history. Remember, Arthur Clarke says by 1992 first have such a satellite. Well, it happened so that by 1963 you had the first communication satellite in geosynchronous orbit. It was called Satcom 1. And then Intelsat consortium was formed in 1964. Intelsat 1 was launched in 1965. So that was 30 years before Arthur Clarke could predict. And then India joined Intelsat, and Indian Intelsat Earth Station was set up in RV 1971. So in this picture you can see Syncom, and in the back you see Intelsat. So how it was used in those early days? This was, I think, to relay the proceedings of I think it was Olympics. So you had, because the very low power satellites were used, for example, Intelsat 1 had just 7 dB watts of power. Now, if you look at other satellites today, they are in several 100 dB watts of power. So 7 was very, very small. And then you had to have these kind of massive earth stations. Typically, look, antenna was 28 meters, and the power which it was pumping up was 3 kilowatts. And to receive the satellite power, it had a low noise amplifier. It was a parametrically cooled amplifier at 50 degrees Kelvin. So the gateway approach was used, and so here you can see how it was used. There is Intelsat 2, which was connecting Japan to San Jose in America, and then to another by landline to Mexico City, and Mexico City was then transmitting the video through ATS-3, which was experimental satellite, to UK, whereas the sound was going on landline, and then using early bird to transmit to a French station called Plumet Houdou, and then everything was being put together so that the UK people could get the both video and audio. So this was so difficult to do in those days. So satellites in fact have been growing very fast. You see Intelsat 1 in 1965, it had 480 for one TV channel. Its bandwidth was barely 50 megahertz. It has a 1.5 year lifetime. RF power was 7 dB watts and two channels. Intelsat 4, which was in 1960, had 8,000 voice channels or 2 TV channels, 500 megahertz bandwidth, a lifetime of 7 years, and RF power of roughly 22 to 29 dB watts, but there were 22 such channels. Right? So you see how the growth has happened over a period of 6 years. So there are several satellite generations, and if you can look at it from the launch years onwards, you see 72 to 79 there were 37 satellites. Then from 80 to 89 there were 96 satellites. 90 to 2002 305 to 325 satellites, and from 2003 there are over 300 satellites. What happens after 2003? This I will cover in my last lecture. So how the operators? So it was earlier, it was only the government, but then now a lot of private operators have come. So you see the number of operators have jumped from 12 to over 70. Of course, when there is market value and other things like that. Interesting point is the lifetime. So lifetime earlier barely 3 to 7 years is now jumped to 12 to 20 years. In fact, nowadays most of the communication satellites have a guaranteed lifetime of 15 years. Also, if you look at the weights, because of the improvement in the launchers, so the weights which are earlier barely 200 going into the 1700 to 6000 kilogram range. And similarly, because the capacity is there, so the power capacity is also increased, and from barely 200 watts it jumped to 750 to 2000 watts. So today, if you look at this diagram, I know most of you will not be able to read it, but the thing is, it shows that in the geostationary orbit, how many satellites are there, which tells you how important is this communication satellites for us in our daily life. So there is something we need to talk about in terms of the satellite beam coverage. Now, we have been talking of satellites, and we said that the satellites are transmitting in a beam, all the power goes into that beam. Right? What has happened is that earlier you used to have what we call as the earth viewing beam. So it didn't differentiate between any different countries or different regions. It was just one big beam, and whoever was in the beam and whoever had the earth station could receive those signals. Right? Something called a global beam. Okay, and this is usually in the C band. Here what you see is what is called a spot beam, and these are now in higher bands is possible. Why? Because in the higher bands, your smaller antenna can have a narrower beam width, and you can now cover a region instead of the entire Earth surface. And then beyond that, now we are having what is called multi-spot steerable beams. That is not only these spot beams, but there are multiple of them, and you can steer them. That is, you can you can move the beam from one region to another. So we will talk about these things much more in the last lecture, but at the moment, please understand that why we have come from the global beam, where everybody can receive the signal, to the spot beams and multiple spot beams. There is a great value in this technology, which we will be covering in the next lecture. So, if you want to look at the evolution of satellite communication techniques, here I have put the years, and here I have put the technology and what techniques that are used, and the frequency band which are used, and examples of those satellites. So, for example, 65 to 1980, you had single polarization global beam. You mainly used frequency modulation. Frequency ranges were in 4 to 6 gigahertz. Examples are Intelsat 1, 2, and 3. 1980, we saw a change to dual polarization and multiple spot beams. It comes in here, and therefore since you have multiple spot beams, you are able to do frequency reuse. That is, since your beams are covering different regions, so the uh, so the uh, so the same frequency can be reused in another which is further away from this spot. So this is the same technology which our mobile people are using, because you have stations separated out, and the same frequency can be reused for the different stations which are farther apart. So this reuse is a technique that comes in. Frequency remains the same. Examples are Intelsat 4 and Inmarsat. In 1990, we started doing what's called beam forming. That is, you did not just have a beam, but you could actually form the beam to cover a very specific region. For example, you can form the beam to just cover India, or you can form the beam to just cover the let's say the Indonesia. So this kind of beam forming was possible, and then we got into the transponder hopping. That is, as I said, you can switch from one transponder to another depending on the requirement. And now the technique was mainly phase modulation. Even frequency modulation was left, phase modulation was used, and frequency now we are up into the 12 to 14 gigahertz band. And typical examples are Intelsat 5 and Eutelsat. Then between 1990 and 2000, we started getting into another technology called switch matrix. What is this? You see, in normal use, what would happen is that you have a gateway station on the ground which would control the satellite and tell the satellite, okay, switch this beam from here to here and so forth, depending on the requirement. Now, this whole idea of the switching was taken up into the satellite, and we are using a technique called onboard switching. Okay, and then by doing this, you are able to now do this kind of technology much better without using a gateway. And this example of this is Intelsat 6. And then 2000 beyond, coming to present days, you are now having scanning beams, inter-satellite links, you are having onboard processing again, and now you are moving into the higher frequency, 22, and also into optical for inter-satellite links. And typical examples of this are the ACTS. This was an experimental satellite by NASA, and Eutelsat, right? So this is how the technology has been. So in summary, in today's lecture, what have we learned? We have learned about the geostationary orbit. We have learned about satellite links. We have learned about parameters relating to satellite links, that like signal to noise ratio, carrier to noise ratio, and antenna G by T. We have tried to understand the link equation and all the various components of the equation. We have looked at noise and how we can aggregate the noise component into one single number called the antenna noise temperature. And then we have looked at the growth of satellites from the earliest ones called Satcom to now the many global satellites that are there. And there are a lot of national and regional systems as well, which we shall talk about later. So that's the presentation.